This is my Lab 5 magnetic braking. So let's just talk about the introduction really quickly. The purpose of this lab was to collect data of a falling magnet through an aluminum tube to observe the effects of Faraday's law and to simulate it and model its behavior on VPython to see if they match our observations. So our findings was that our experimental time and calculated time were very similar. The experimental time was 1 second, but the calculated time on VPython was 0.977 seconds. So, some relevant formulae and concepts. There's the Faraday's law, the Biot-Savart law, the magnetic field of a bar magnet, and the Newton's third law. So, with this, the first part of this was that we had to do the experiment. With this thing, we had the falling magnet. We used a roll of aluminum foil to just like drop the magnet in, and we have our calculations on the right, and the mass and the magnitude of the dipole moment is also on the right as well. We repeated this process 5 different times, and we had an average of 1 second. So assumptions and sources of error was that the experiments were done through an online model. The experiments were done both on an online model and in real life, so there are sources of human errors that we could have made. And another assumption that we made was that this tube always stays fixed. So with the data, we modeled this data in VPython, where we first defined all of the values that we had from before. Which was like the length, the width of the foil, as well as the mass of the magnet, as well as the magnitude of the magnetic dipole moment. We calculated the dipole, the magnetic field of the dipole, which was calculated in Lab 3. Next up, we calculated the d flux dt through each ring of the falling magnet. This was calculated by using the formula above over here, which basically calculates the d flux by getting the ring, the distance, speed, and calculating df dt by dividing the numerator with the denominator. And we set the current to be equal to the d flux dt over the ring's radius, so it shows the flux through the ring. And moving on, this one is calculating the b at the ring. We calculate the b hat, we calculate the sine theta, making sure that we have the correct dot product with the flux. The f mag f on ring basically calculates that, and we have the force of gravity, which is counteracting, which is basically causing the magnet to fall down, but the F net is the F grav plus the F magnetic, which is forcing it upwards, and we calculate the velocity of the bar magnet by the formulas below and the position as well. So with this, we were able to see a graph where the bar was able to fall down fairly quickly, but then slow down as the force of magnetism was pushing up against the force of gravity, and this was very close to the time that we modeled of 0.977 seconds. And we're just going to move on to the questions at the end. If the resistivity of the conductor was reduced to close to 0, the braking force would increase until it balances out the force of gravity. This would increase the time that it would take for the magnet to fall to the ground. And what if there are holes or slots cut into the tube? This would basically break the rings of currents in the tube, which would lessen the braking force, causing the magnet to fall faster.